Okay, so today's class we will look at some examples of the use of Fourier transforms. We already saw in the last class one example of how you can use Fourier transforms to solve differential equations. Now, today we look at an example where which has an important role in quantum mechanics, and this has to do with what is called the position and momentum basis. So, okay. So, one of the postulates, in one of the first postulates of quantum mechanics is that you describe the state of a system by a wave function psi. Okay. You describe the state of the system by a wave function psi that is a function of the spatial coordinates. So, if you have a one dimensional system, this will be a function of just x, the spatial coordinate. Okay, so, this describes the state of the system, and if you have any observable, okay, then that observable corresponding to that there exists an operator. So, this corresponds to, this is operator corresponding to observable. And I'll say physical observable. And this physical observable could be the energy of a system, could be the momentum, could be the angular momentum, could be anything. Okay. So, this is the operator corresponding to the physical observable, and if you have an operator acting on a wave function, then this gives you some other function, gives you psi prime of x. Okay. So, it just gives you some other function. So, this is some other function. Okay. But corresponding to psi, but there exists phi of x, phi, I will say phi o of x, okay, for operator O, such that operator acting on phi of x is equal to lambda O times phi O of x. Now, lambda A is a scalar, okay, and it is a real number. So, if this corresponds to a physical observable, this is a real number, and this operator is what is called Hermitian. So, this is a Hermitian operator. This is a scalar or a real number. Okay. Then phi 0 is called the Eigenfunction of operator O with eigenvalue lambda O. Okay, so this is so one of the postulates of quantum mechanics is that corresponding to every physical observable there exists an operator, okay, and this operator has eigenfunctions and eigenvalues. The eigenvalues are real, and it furthermore these eigenfunctions they form a basis. So, eigenfunction set of phi 0 of x forms a basis. Okay. So, this is one of the fundamental postulates of quantum mechanics, and when you say it forms a basis, that means if you have an arbitrary psi of x, you can write this as a sum over all the what did I call the eigenvalues? All the lambda O's, or sum over I will just say I, lambda I, phi I of x. Okay. So, that means phi I of x, where this is eigenfunction of any operator with eigenvalue lambda I. Okay. So, you can choose any operator, you can choose eigenfunctions of any operator that corresponds to a physical observable to do this basis expansion. This is the usual basis oh, I should not call this lambda I, this should be C I. C I. Okay. So, C I phi I. Now, since this is an eigenfunction of any operator. So, if that operator, okay, so we'll just leave it at this. So, in other words, operator on phi 0 on phi I is equal to lambda I phi I. Okay. Then furthermore, the theorem of quantum mechanics says is that when you take a system in this state, when you take a system in this state and you measure the value of operator. So, operator O corresponds to the physical observable. When you measure that physical observable, you will see one of the eigenvalues. So, in any measurement you see one of the eigenvalues, okay. And the probability of seeing this eigenvalue lambda I. So, probability of measuring of rather let us say observable, of observing lambda I in a measurement is C I square. Okay, that corresponds to absolute value of C I square. Okay. So, absolute value of C I square divided by I C I square. Okay. So, it is suitably normalized. Okay. So, you take absolute value of C I square divided by sum over I C I square. Okay, and this will just be some constant number. So, it will just be it is proportional to absolute value of C I square. Okay. So, let us look at a specific example of this. So, let us take example operator is equal to P operator in one dimension. So, I will use P, this is minus I h cross d by dx. So, it is the operator corresponding to, so that is the form of the operator. So, what are eigenvalues? Are eigenfunctions of the operator. Okay. So, the general form is the following. So, what you will say is that P operator operated on phi, I will call it phi P of x equal to eigenvalue, the eigenvalue of P I will just call it P phi P of x. This is the eigenvalue. Okay. So, eigenvalue is some momentum, that means you make a measurement and your value of momentum is P. Okay. So, P is an eigenvalue. So, now we have to solve this equation substituting this value for operator P. So, you have minus I h cross d phi P of x by dx is equal to P phi P of x. Okay. And if you bring the phi P on this side, you take the dx that side, you integrate it, what you will get is the following: phi P of x is equal to e to the I P divided by h cross x. Okay, it is proportional to this, right. So, you can take this value now. Now, if you take this, then you can clearly see that if you take the derivative, you will get I p by h cross, okay. And if you multiply it by minus I, you will get 1, and h cross you will just get p. So, clearly is equal to p phi p of x. Therefore, p operated on phi p of x is just p times phi p of x. So, this is eigenvalue, and this is the eigenfunction. Okay. So, you notice that the eigenfunctions are just e to the I this eigenvalue divided by h cross times x. Okay. Now, this looks a lot like I k x that we were doing in the Fourier series. Okay. So, let us go ahead and see what this implies. So, suppose since phi p of x, since the set of all phi p's of x forms a basis. Okay, so, what I mean by this curly bracket is a set of all phi p's of x, this forms a basis. Okay. We can write psi of x, okay, any arbitrary wave function is equal to sum over all values of p, coefficient C p phi p of x. Okay, so, you can write it in this form. So, this is just sum over p C p e to the I p by h cross x. Okay. Now, again this looks very much like the Fourier transform. Instead of having if you had a p by h cross here and a p by h cross here, then everything would have been the same. So, we say let k equal to p by h cross. Okay. Then I can write this expansion in the following form: psi of x is equal to sum over k c k e to the I k x. Okay, c k e to the I k x. Okay. So, this looks exactly like a Fourier series. Okay, so, this looks like a Fourier series. Okay, only thing is we have not put any boundary conditions. We have not specified what the boundary conditions on this wave function is. Okay. Now, in case you say that the wave function should be periodic with some time period, then this will be exactly the Fourier series with that period. Okay. In case you say that the wave function need not be periodic, it can be the space is infinite, then what we will show is that this sum becomes an integral. So, we have two cases. Case 1, psi of 0 equal to psi of L equal to 0. Okay. So, this would be one case when the wave function is periodic. So, this is periodic wave function. Okay. So, in this case your psi of x to 1 over or 2 over L integral 0 to L or sorry, and psi of x looks like sum over k c k k x, okay, where k equal to n pi by L. Or sorry, 2 n pi by L, 2 n pi by L, because L by 2 is the periodicity. Okay. So, then this is exactly the so k So, implies k is equal to 2 pi by L, 4 pi by L, 6 pi by L, and so on. Okay. So, this becomes exactly so this is a Fourier series. Okay. So, if you have a system with such conditions, so that is confined to some length, okay, then you can expand your wave function as a Fourier series. Okay. And this is a typical this is very common in seeing the one dimensional problems where you do not have any potential, then you would often represent it by a travelling wave. Okay. So, this corresponds to the travelling wave solutions. So, this is your travelling wave with momentum p. So, that is your psi of x. Now, case 2, okay, no boundary conditions, free particle. Now, in this case your psi of x, so free particle, and this implies your k can take any values, arbitrary values. And in this case your psi of x, since k can take arbitrary values, your sum over k can be continuously varied. So, your sum over k becomes an integral dk. Okay. Now, c is a, since k is a continuous function, I can write c of k as e to the I k x, and instead of c of k varies continuously. So, I will just call it some function of k. So, let's call it some function of k. No, okay, let me not use psi, I will use psi tilde. Okay, and you can clearly see what we are trying to do. So, from going from this continuous in this discrete, when the k values were discrete, you had a sum, okay, in which naturally corresponded to a Fourier series. Now, in the case when there are no boundary conditions, free particle, k can take arbitrary values, this sum becomes an integral, okay, and this c k gets changed to some function of k, because k is continuously varying. You have, so the c k can be represented as some function of k. We call that function psi tilde of k, okay, and it is clear what psi tilde of k is. So, psi tilde of k is Fourier transform of psi of x. Okay. Psi tilde is Fourier transform of psi of x, and this is called wave function in momentum representation. Okay. And this is your wave function in position representation. So, this is wave function in position representation. Okay. So, what we see is that the wave function in the momentum representation is the Fourier transform of wave function in position representation. Okay. Now, physically what this means is that what your psi k corresponds to. Psi k you should really think of it as the coefficients, Now, what do these c k correspond to? If you have discrete, then if you have a discrete set of k values, okay, then ck square corresponds to the probability that in a measurement you will observe value of momentum of k. Okay, so remember this c of k. So let us see. So when we write psi of x is equal to sum over, well I will go back to my p, since p is Cp e to the I p x by h cross. So we had this, right. That means your wave function is written as a superposition of eigenfunctions of momentum. The eigenvalue of momentum corresponding to e to the I p x is just p. So then you ask a question, what is the probability of observing momentum value p. So that means you make a measurement, okay, you will get one of the eigenvalues. What is the probability of getting momentum value p? The answer is just Cp square, okay. So it is proportional to Cp of Cp square. So probability proportional to Cp square. This is the probability of observing momentum p. Okay. So now you go back to this. So when we say that psi tilde of k is the Fourier transform of psi of x, okay, then and we have this sort of representation. So that means probability of observing wave vector k is equal to psi tilde of k square, okay, and this is just okay. So what is the probability that you will observe wave vector k? That is just psi tilde of k star psi tilde of k, which is just based from by comparing with this. Okay. So now you understand why psi tilde of k is called the wave function in momentum representation, because if you want to find out the probability of finding a certain momentum, you just do psi star psi, okay, in this representation. Just as probability of observing position x. So probability of observing position x, that is the probability that your particle is at x. This is just psi of x square is equal to psi star of x psi of x. Okay. So now you can see why this is called wave function in momentum representation. This is wave function in position representation, because the probability of observing position x is just psi star psi. Probability of observing position x is what is the probability that your particle is located at x, okay, or located between x and x plus dx, okay, that is psi star psi dx. Okay. So this should stay a little corrected. So this is now this is density. So this becomes probability density. Okay. So now when you go to discrete variables, when your values of momentum can take only certain values, you can talk about probability, but when your values of momentum can be continuous, then you have to talk about probability density. So all these are so just as psi star psi represents a probability density, that means probability of observing position between x and x plus dx is equal to x dx. Okay, so this is the probability of observing position between x and x plus dx. So, because x is a continuous variable, you cannot ask what is the probability of observing position x, you have to ask what is the probability density of observing position x, or you can ask what is the probability density at x. Okay. So, what we have seen is that this momentum representation is is a Fourier transform of the position representation. And now we can go ahead and ask the next question, what are the eigenfunctions of position vector, okay, or what are the eigenfunctions of position operator. So, what are the eigenfunctions of position operator? So, let us take the case where you have no boundary conditions and we want to find out what are the eigenfunctions of the position operator. What are position operator? Okay. So, then if you have phi x of x or phi x 0 of x, okay. So, you will say x operator on phi x of 0 of x should be x 0 times phi x 0 of x. So, this is the eigenvalue equation. Okay. Now, x operator is just x. So, x multiplied by phi x 0 of x is equal to x 0 times phi x 0 of x. Okay. So, the eigenfunctions of position operator are such that when you multiply by x, it is the same as multiplying by x 0. So, this is the eigenvalue. That means, when you make a measurement of position, you ask where the particle is, your answer is x 0. Okay. So, the probability of getting x 0 is related to phi x 0 square, or the coefficient of phi x 0 square. Okay. So, now we have to find out what phi of x 0 is, and we can do it the following way. So, to do it, we say psi of x is equal to sum over x 0 c x 0 phi x 0 of x. Okay. And since x 0 can take all values, okay, so this becomes equal to integral dx 0 c x 0, I will just call it as, okay, I will just say c x 0 phi x 0 of x. Okay, this is psi of x. So, probability density of observing position x 0 is equal to c x 0 square. Okay. But you know that c x 0 square is nothing, should be equal to psi of x 0 star psi of x 0. Okay. So, c x 0 square should be nothing but psi x 0 star psi x 0. So, in other words, c of x 0 should be equal to psi of x 0. Okay. Right. So, in other words, c of x 0 should be nothing but psi of x 0. So, that c of x 0 square is psi star psi or psi square. Okay. So, in other words, you have psi of x is equal to integral dx 0 psi of x 0 phi of x 0 of x. Okay. And when you look at this form, you would immediately recognize that this is satisfied if, so implies phi of the function that satisfies this. If you remember, when we were discussing delta functions, we said that a delta function is one such that when you integrate dx0 of psi x0 delta x minus x0, you get psi of x. So, that means phi of x0 of x is equal to delta x minus x0. So, what we have concluded is that the position basis functions, your basis functions of position operator with eigenvalue x0 are just delta function of x minus x0. Okay. And this makes sense physically also, because if you had delta f x, if you want to say that you are in a state which has a very fixed value of the position, okay, then the only state that can have a fixed value of position is where your probability of finding the particle is only non-zero at one point. Okay. So, psi has to be equal to delta x minus x0. See, suppose you have suppose this is your x variable and this was your wave function. Now if you had a wave function like this, okay, then you have a certain probability of finding it here, certain probability of finding here, certain probability of finding everywhere. But if your wave function looked like this, this value of was x0. So, a delta function at x0, then the only place where you can find the particle is at x0. Okay. So, therefore, when you make a measurement, you will get one specific value of x0, and that is why this is an eigenfunction of the position operator. Okay. So, eigenfunctions of position operator are delta functions, and you can easily see that if you write psi of x is equal to you can trivially see that that if I put delta functions, then this equality gets satisfied. So, what we saw is the following: psi of x, if you write psi of x is equal to sum over x0 c of x0 phi x0 of x. Okay, this is a basis function expansion. Now, we saw that phi x0 of x is equal to delta x minus x0. Okay. And what you will say is that c of x0 is equal to integral psi of x phi of x0 of x dx. Okay. And this is nothing but c of x0 is nothing but psi of x0. Okay. So, so now probability of observing probability density of observing x0 is equal to c x0 square, and this is equal to psi of x0 star psi of x0. Okay. So, this is consistent with the Born interpretation of wave function. Of wave function. Okay. Okay, so this is completely consistent with the Born interpretation of wave function. Okay. And last thing I want to say is that in this aspect is that we saw that the position representation and the momentum representation are Fourier transforms of each other. Now, that can be understood in a very simple way. So, a momentum representation. So, if you look at the eigenfunctions of momentum, they are e to the I p x by h cross. So, this is your eigenfunctions of momentum. Okay. Eigenfunctions of position are delta x minus x0 x. Okay. So, what that means is the following: the eigenfunctions of momentum. Okay. So, if you have a definite value of momentum, if you want to have a state where the value of momentum is definite, that state should look like this, and if you just take the real part of this, it just looks like a cosine wave. So, it will look like this. Okay. So, this is a state with a definite value of momentum. Okay. So, notice that if you have a state with a definite value of momentum, it can be found anywhere. So, the particle can be anywhere. Okay. If it has to have a definite value of momentum, it has to be it can be anywhere. Okay. That means you know nothing about its position. So, that means if you have a definite value of momentum, you know nothing about the position of the particle, okay, because it can be anywhere. On the other hand, if you have a definite value of position, then what you do is the Fourier transform. What you do is a definite value of position will look like this. So, this is x 0. Okay. So, this is a wave function that has a definite value of position. Okay. So, what you can show is that if you want to write this in terms of momentum basis, you have to write this in terms of infinitely many momentum. So, if you have a definite value of position, okay, you can write delta x minus x 0 is equal to sum over p c p e to the I k I, well, we can write this as integral dk psi tilde of k e to the I k x. Okay. So, I can write it in this form, and basically what it means is that in order to represent this function, you will need infinitely many wave vectors. Okay. So, what you will find with this is that psi tilde of k is equal to x 0. Okay. That means for any value of momentum, okay, so this implies psi tilde of k star psi tilde of k is equal to 1 for any k. That means you can have wave vector be any value. In other words, you can have momentum take any values. Okay. So, all values of momentum are possible. So, if you fix your position at x 0, then you can get any value of momentum possible. Okay. So, in a sense the whole idea of uncertainty principle is contained in this Fourier transform. Okay. So, this is one very common application of Fourier transform. The other application that I will just mention briefly about Fourier transforms is the power spectrum. Okay. So, the last application I will just mention this briefly. This is the power spectrum. This is example is FTIR or FTNMR and so on. So, you might have heard this is Fourier transform infrared spectroscopy. Okay. So, what is the role of Fourier transforms in spectroscopy, and this I will just mention it briefly, I will not go into too many details. This is based on the Parseval's theorem. So, Parseval's theorem says that that integral f of x square dx is equal to integral f tilde of k square dk. Okay. Now, when you do in any spectroscopy, okay, so in any spectroscopy what is done is the following: you have a sample, this is a sample, okay, you shine light of a certain frequency. So, you shine light of a certain frequency, and light of a certain frequency can be that corresponds to an electric field that has the form E 0 omega t. So, the electric field oscillates in time with this frequency, with this angular frequency, and you can already see that since the electric field is an oscillating function in time, you can already see that something like Fourier transform might be useful. Okay. So, when you shine a light now then you record, you send one frequency omega, check for absorption. Okay. So, you check for absorption and you see whether it absorbs at that frequency. Okay. Then what you do is you change the frequency, okay. Check for absorption at frequency omega. Okay. Then what you have to do is you need to change the frequency and send another frequency and then again check for absorption. You keep doing. So, repeat for all frequencies, okay, and construct spectrum. Okay, so for example, you could say the absorbance as a function of frequency looks like this. So, so you have various frequencies. Okay, I should probably just show them in the positive direction. Okay, so you look at a particular frequency, you will see very low absorption. Maybe at some frequency you will see high absorption. You will see things like this. So then you connect all of them and you will get some spectra that looks like this. Okay. Okay. Now you can see that this is a very tedious procedure, because you have to send one light of one frequency, then another frequency, and then you have to keep sending lights of different frequencies, okay, to measure this. So, this is very tedious. Okay, not only do you have to send light of one frequency, then send light of another frequency, then keep changing the frequency, and so you have to keep changing the light and check the absorbance. Okay, now this can be very tedious. So, one way to get around this, you use Fourier transform FT. Okay. So, the idea is and this is where we will use the Parseval's theorem. So, instead of doing it in the time domain, we will do it in the frequency domain. So, we use the Parseval's theorem. Theorem says integral equal to integral e of omega square d omega. Okay. So, this is how much of the intensity of electric field, okay, how much electric field is absorbed at time t, okay, that is related to. So, the integral under that is related to how much light is absorbed at a particular frequency. So, this is at frequency omega. So, this E of omega square is how much light is absorbed at frequency omega. If you integrate over all omega, that is same as this is how much light at time t. Okay. So, then now the strategy is very simple. So, you just send lights, of different time duration. So, instead of sending light of a single frequency, you send lights of various time durations. So, you send various pulses of different time durations, okay, and you program it in such a way that you know what this distribution of frequencies is in each pulse, okay, and you just measure how much of the total light that is being absorbed. Okay. So, you measure the total light that is being absorbed as a function of these pulses, okay, and you can use the light. So, use light pulses containing a mixture of frequencies. Okay. In this case you sent a light of only one frequency, only 1 omega, but in this case your light, you are sending a pulse that has a mixture of this is a sample of many frequencies. Okay. And you send a pulse of a certain duration and you measure and you see absorbance as a function of time duration. Okay. So, as a function of the time duration of the pulse, you can see how much light is absorbed. Okay. And from this you can take the Fourier transform, you can Fourier transform that information to get how much light is absorbed at a certain frequency. And this on the other hand is much easier to do, because you do not have to keep sending different frequencies, you just send lights of different pulses, okay, with a mixture of known frequencies. Okay. So, there are more details in this, but I just wanted to mention that Fourier transforms are very useful in spectroscopy. Okay. So, with this we conclude the discussion on differential equations and applications, and starting from the next class we will start talking about a completely different topic, that is group theory.